and how they'll benefit both exploration and science. What I want to do is show you the instruments that are aboard LRO, describe to you how the measurements will be made, and then give you a preview of some of the data products that we expect to have from LRO. The first video, this shows the LRO spacecraft, and on the left-hand side shows the spacecraft in development with the instruments being installed. Crater is our radiation sensor that will measure the energetic radiation environment that may be damaging to astronauts with an innovative sensor. The next instrument shown is Diviner, our infrared radiometer that will measure with great precision for the first time the temperature distribution around the lunar surface, including the very cold regions at the poles. We have an advanced laser altimeter called LOLA that fires 5 laser beams at the lunar surface 28 times each second in order to measure with very high precision the three-dimensional profiles of the surface. We have a set of cameras. This shows the high-resolution, narrow-angle camera on LROC and them being installed. There's also a wide-angle camera that will measure the global surface of the moon. We have an ultraviolet spectrometer called LAMP that measures water frost on the lunar surface in the cold regions, and will look for minerals on the surface. And then we have a neutron detector, which is a contribution from Russia, which will measure with great resolution the hydrogen content of the lunar surface. And then finally we have a technology demonstration experiment called Mini-RF, which is an advanced synthetic aperture radar. It is a more complex, advanced version of a system that is now flying on the Indian spacecraft Chandrayaan. This shows the spacecraft in the environmental testing at Goddard prior to shipment to the Cape. The spacecraft is here now. We're ready to go for launch, and the science team is ready. We have here in the audience today the scientists responsible for each of these instruments, and they'll be available to talk to you later if you have any questions for them. LRO will carry these 7 instruments to the moon. One of them, the radiation sensor, measures directly the lunar environment. The other 6 instruments are remote sensing instruments. The next video shows for you how these measurements will be made. LRO goes into a very low altitude circular polar orbit. Every 2 hours it maps the moon with the instruments pointed downwards, and each of the cameras are narrow angle, and the measurements are over a very small portion of the lunar surface. But as the moon rotates with a period of 1 month, you can see that the surface beneath the spacecraft is mapped out. Now the moon rotates in a period of 4 weeks, and so every month we will map the entire surface of the moon. And there are gaps in our measurements because of the fact that the view of the instruments is fairly narrow beneath the satellite ground track. However, you can see here the first 1 week's worth of data. We've mapped out roughly half of the moon, and over the course of an entire year we'll be able to fill in these gaps so that we will have a global measurement of the moon and have a new set of data, essentially a new atlas of the moon that has not only measurements of topography and temperature, but minerals, and then global images of the moon. Now, Mike indicated that one of our primary objectives is to identify safe landing sites for future human return to the moon. The Apollo program accepted risk and was able to have safe landings, but we want to return to the moon, make repeated landings in some areas, and be able to go there with a higher degree of safety. Now, some of the concerns we have are the unevenness of the surface, rock distribution, boulders, and craters. So the next video shows you how the LRO data sets will help safe landing. The first panel shows topography as measured with our 5-beam laser system, and then in green it shows areas that are level and would be appropriate for landings. The next panel shows temperature maps, and from the temperature variations with solar illumination we can determine rock abundance. In here it shows areas that have rock abundance that are not suitable for landings. And then finally, just as an example, you can see the images of this region with high resolution. Our camera has a 50-centimeter spatial resolution, so we can see very small boulders and know where it is safe to land. And then when you combine all of these data sets, if this region is one that we would like to land, we can identify the areas that are safe for human landings, and then the astronauts could land there, here shown in green, and then explore the region after they land. Now, we have worked with the Constellation program to identify 50 high-priority sites where we would be potential landing places for astronauts. These will be dedicated regions of the highest priority for our high-resolution measurements. Because of the data rate required with these high-resolution measurements, we will only map a small portion of the moon in our first year. We are also working with the science community to identify other regions that are of great interest to the science community, and we will make those data available in all of the data we obtain to not only the exploration planners, but the U.S. scientists and the international science community. Now, let me give you an example of one of the maps that we expect to obtain. Right now we lack a high-precision three-dimensional map of the lunar topography. The next video, this shows our familiar moon as we see it, but what we would like to have is a three-dimensional relief map that shows the variation in the surface altitudes. This image is based on the best available data. You can see it's somewhat fuzzy because the data in the low latitudes have only 1 point every 30 kilometers. LOLA will give us data that has roughly 1,000 more data points. This shows the crater Tycho, which has been mapped with ground-based radar. It has a higher resolution, but our LOLA measurements will be at least 10 times better than this. So we'll have much sharper relief maps of the moon that will enable not only science analysis but help exploration planners. The graph here the image has moved over to the polar regions. This is a region that is of high interest to us because we think that it is a excellent candidate location for future human returns to the moon. We think there may be resources in this region. We now swing over to the South Pole Aitken Basin. This is a large depression near the South Pole, and it's a site of keen interest to the science community, and so we are looking forward to mapping that region very carefully. So at the end of our mission, we will have a new atlas because we will have new eyes on the moon with LRO. We will get new views of the moon, and we will prepare for the next generation of explorers and scientists the handbook, the guidebook for future exploration of the moon. Now, I mentioned the fact that we think there may be resources at the polar regions. We know that there is one important resource there, and that is nearly continuous sunlight. The next video shows you why this is true. Here we see the moon going through its day-night cycle once a month. At the equator, daytime is 2 weeks long and nighttime is 2 weeks long.